Well, in today's lesson, we are going to look at two additional examples of optimization. You notice the problems will get a little bit more challenging, but you'll have two additional examples to help you with analyzing future problems. So you can see here we've got a situation where we have to lay cable and we have a river. So the river is kind of, whoa, I need to switch to pen mode. There we go. Let's make this blue for river. So we've got the river here, okay? And what we want to do is we want to lay a cable, and it has to go from point R. We're going to go across the river and then along the land, and it has to end up here at the end of point T. Now the cost for laying cable varies. For land, it's $10,000 per kilometer, but underwater it's more expensive. It's $16,500. So we want to locate this point P at such a place where we will minimize the cost of laying the cable. Okay, well, knowing that, then let's go ahead and use our protocol, our graphic organizer, to help us solve this problem. So, I keep forgetting to switch to the hand mode when I need to move things. Here we go. Okay, and let me get rid of this mark. It's annoying. Okay, so the question is, at what point should I lay the cable to minimize the cost? That's what we need to find out. So actually that is what our variable is going to be, because we need to be able to find the distance from S to P where I'm going to place that point. So here we go, hand. So this is what X is going to be, is this distance from S to P of where we will lay the cable. So if the whole distance is 4, then the distance from P to T would be 4 minus X. Okay, so X will represent, X is distance from S to P. Okay, great. This line here is bugging me, so I'm going to erase it if it will let me. Nope, it won't let me. Okay, how about if I just go like this? There we go. Okay, my little perfectionist side. Now, let's continue looking at. So the facts that we are given, we know that the distance from S to T is 4, and the distance from S to R is 1.2. Land is $10,000 per kilometer. Water is 16,000 kilometers. So what we have to do then is we have to find the cost for this. So the cost is going to be 16,500 for the distance along this hypotenuse of the triangle. So that would be times the distance h. Then we're going to add it to $10,000, and then it would be this distance here. So that would be 4 minus X. Now we've written an equation, but you see that we're using two variables here. We have X and we have H. So we need to rewrite it so that it's in terms of one variable. Well, looking at my diagram, I see a familiar shape, using our geometry skills. We see a right triangle here, and using Pythagorean theorem, we can find the length of H. So Pythagorean theorem is 1.2 squared plus x squared will equal h squared. So if we simplify that, then we're going to get 1.44 plus x squared is equal to h squared. So therefore h will be the square root of 1.44 plus x will equal h. So let's go ahead and replace then into the original function that value. So 16,500 times h plus 10,000. Oh wait, why did I write plus h? I didn't want to do that. The value of h is the square root of 1.44 plus x squared. Sorry, this square did not come down with it. There we go. And then we're going to add that to 10,000 times the quantity 4 minus x. So now we have written an equation for cost in terms of one variable. So now that we've done that, Now we have to take the derivative of this, of course. Woohoo! Okay, so scrolling down here, now let's find the derivative. Okay, derivative of cost will be equal to, so we're going to have 16,500, and then we're going to bring the 1/2 in front, and then it will be the quantity inside, which is x squared plus 1.44, and that will be raised to the negative 1/2, and then times the derivative inside, which would be 2x. And then that will be plus, then we take the derivative of that, which would be negative 1 times 10,000. So actually it's a negative 10,000. Okay, great. Now continuing on along, let's simplify this a little bit. So we've got this 2 and this 2 will reduce. So I'm going to be left with 16,500x in the numerator all over the square root of x squared plus 1.44 minus 10,000. Now, because we're looking at critical points, we need to decide when the numerator and denominator is equal to 0. So we need to simplify this equation so that it's a rational equation. So the common denominator will be the square root of x squared plus 1.44 and 16,500x minus, and then we would have to multiply it by the common denominator. So it's going to be 10,000, then the square root of x squared plus 1.44. So now we have our first derivative. So now we must take this first derivative and find the critical points. So we could set the denominator equal to 0 and set the numerator equal to 0. Now I'm kind of running out of a little space here, so I'm going to erase a little bit of the work. So hopefully you have written it down into your paper so you won't need this anymore. Okay, so let's look at the numerator set equal to 0. 16,500 minus 10,000 square root of that quantity is equal to 0. Sorry, I just ran out of room there. So I'm going to subtract 16,500 from both sides. 10,000 x squared plus 1.44 is equal to negative 16,500. Divide by 10,000. So now we have square root of x squared plus 1.44 is equal to, let's see, it's now positive 1.65. Oh, I'm sorry, that was an x, sorry. 1.65, that was x. 1.65x. Okay, and then we'll square both sides. So now we have x squared plus 1.44 is equal to 2.723 x squared. Okay, I'm going to erase a little more so I can give myself some room. Okay, because I took care of the numerator, I set that equal to 0. Okay, now in continuing, we are going to then subtract x squared. So now I have back to the pen. 1.44 is equal to 1.723 x squared. Divide by 1.723 and take the square root, and I end up with 9/10 is equal to x. Okay, so that'd be 9/10 of a kilometer is where we would place P. Now we also have to consider the denominator. So if we were to set the denominator here equal to 0, so we'd square both sides, so we get x squared plus 1.44 equals 0. And then you notice we're going to get x squared equal to a negative 1.44. Well, we know that's an imaginary root, so we'll not consider that critical number. So our value of where we would place P is 9/10 of a kilometer away from S. Okay, now did you answer the question? Yes, we found the location of P. Correct units, yes, 9/10 of a kilometer. And is it in the domain? Yes, it is. Very good. Now let's do one more problem, and then you'll be off to try your 2 problems. So we're going to talk a little bit about some application in economics. Now just some basic terms that you need to be comfortable with is, first of all, knowing that we're going to let R of X represent revenue. That is the cost. So like if you sell it for $20 and you sell 10 items, then your revenue is $200. C of X is the cost to produce, to manufacture. And P of X then is your profit. So that would be the difference between revenue and cost. Now to maximize profit, we would set the derivative of profit equal to 0. Another way of thinking about it, it's the derivative of revenue minus the derivative of cost equal to 0. Or we could say, when is the derivative of revenue equal to the derivative of cost? So those are some kind of basics in looking at problems of this sort. So our first situation here is, let's say we've got two functions that model our profits for our company. So the revenue is 9 times the X, which is the amount of units, thousands of units sold. So your revenue is, you make 9 times that of the amount of units you sell. Now your cost is modeled by this cubic function here. So this is the cost for making your units. And what you want to know is there a level of production where I will maximize my profit? Okay, if so, what is it? So let's take. So here we have our graphic organizer, and the question we want to know is, what is maximum profit? So we want to write an equation for profit in one variable and then take the derivative. We know the revenue is 9x and the cost of x is this cubic. So then profit is going to be the difference between revenue and cost. So profit will be 9x and then subtracting cost, x cubed minus 6x squared plus 15x. Now this is quite nice because we notice our equation already is in terms of a single variable. So if I were to combine like terms and such, I'm going to have negative x cubed and then positive 6x squared, and then 9x minus 15x is negative 7x. Wow, this isn't so bad, is it? So now to find the maximum profit, we're going to take the derivative of the function, and then we will set that equal to 0. So negative 3x squared plus 12x minus 7. Okay. Well, unfortunately, this does not look like it is a factorable equation. Negative 3x squared plus 12x minus 7. So either with my calculator or using the quadratic formula, then I must solve for x. Well, in doing my calculations, I found two values of x where the derivative would equal 0. And the two values I found was x equals 0.709 and x equals 3.29. Now this is thousands of units, okay, thousands of units. So I have to decide which one is the maximum I would want to produce in order to maximize my profit. So if we were to look at a sign chart then for this, so 0.709 and 3.29. So if we were to substitute a number less than 0.7 into the function, for example 0, I say that I get a negative. And if I substitute a value of 1, negative 3 plus 12 is 9, minus 7 is positive. And then if I substitute a value greater than 3.29, like 4 squared 16 times negative 3 is negative 48, plus 48 is 0, minus 7 is a negative. So we can see then our maximum is where we change from positive to negative. So at 3.29 thousands of units of production, I will reach my maximum profit. Okay, so did we answer the question? Yes, we found the value of x that we need to produce to maximize profit. Unit is in thousands of units, and yes, it is in the domain. So now you go ahead and try the two problems that were assigned to you, showing all of your work through the process of optimization.